Hello and welcome. In this presentation, I'll be talking about the control charts for variables. Now, control charts for variables are useful when an organization has performance measures that can be quantified, that can be measured on an ongoing basis. So, the control chart for variables can be of two types. You could have R charts or they can be XBar charts. Now, R charts where R is nothing but the range. So we need to keep this in mind that we are really looking at the range. And range is essentially maximum value that we have minus the minimum value. Right? So for every sample that we collect, these are measured performance variables that we have. We will have a maximum value within that sample and the minimum value within the sample. We take the difference of the two, that will give us the range. And the objective of these R charts is to basically ensure that the process variability is in control. You don't make products or services are not being created with too much variance in it. And the way an R chart has to be constructed is that you have to determine what the upper control limit and lower control limit for that R chart should be. And to get the upper control limit, we have a formula, which is D4 times R bar, where D4 is essentially a constant. This constant is something which we get from a given table, and that table is available, which we can utilize to calculate these numbers. It provides the constant for 3 standard deviation limits for a given sample. So it's a given number that we are utilizing here, D4. R bar, on the other hand, is the average of several past range values. So we keep collecting these range values for all the sample, maximum minus minimum, and then we take an average of all the range values that we have, and therefore that bar signifies that we have the average of the range. So that's the way we will then get the upper control limit multiplied D4 with R bar. And lower control limit is D3, which again is a constant coming from the same table from where you get D4 and multiplying it with R bar. Now, XBar chart, these are the charts which focus on the average output that a process generates. To get an XBar chart, we need upper control limit and lower control limit. And there's a certain formula that we have to use for getting these two numbers, upper control limit and lower control limit. The upper control limit is X double bar plus A2 times R bar. And lower control limit is also X double bar, but minus A2 times R bar, where this X double bar is essentially the central line of the chart, which is the average of all the past sample means. So the reason we have this double bar is because it's an average of averages. So we have sample with different values within the sample. We take the mean of that, and we have several samples that we have collected. For each of them, there is a mean. Now, what we are doing is we are taking the average of all these means, which is average of averages, therefore X double bar. This value of A2 is again a constant, which we get from the same table that we used to get D3 and D4 values for our R chart. And R bar, we saw in the previous slide, is nothing but the average of the range that we have for all these samples that we have collected. Now, we'll take an example to get a better understanding of it. But before we get to the example, this is the type of table that we will be utilizing, where we have the value for A2, which is necessary for XBar chart. We have the value for D3 and D4, which are necessary for R chart. Now, notice that these values that we see are corresponding to certain sample size. And this is something which we need to be very careful about. Which of these rows we want to use is dependent on how many values or how many units are there in a sample. And we will see this in an example in terms of understanding how we determine which of these value of A2, D3, and D4 we should be using. The steps to control or to create a control chart or compute these upper control limit and lower control limit is to collect the data. Then we compute the range, because the range is something that we need for both R chart and XBar chart. And then using that table that we just saw, we determine the R chart control limits, because once we know the range, we can find the R bar and utilize the formula that we had. We then plot the sample ranges in that R chart that we have constructed. If all the values are in control, then we will move to the next step, which is step number 5. If all the values are not in control, then we have to find the assignable cause for why we have certain values that are outside this R chart control limits. We correct them, and then we return back to step 1. So 1 to 4 has to continue repeating until we are comfortable with the R chart being every value is in control as seen in the R chart. Once that happens, we go to the XBar chart, and there we calculate XBar for each sample and determine the central line of the chart, which is the X double bar. And then once we determine that, we can utilize the formula to get the values of A2 from that table and substitute that in the formula to get the control limits for the XBar chart. Now we plot the sample means on the XBar chart. If everything is in control, then the process is in statistical control, because both R chart, we find everything is in control, and in XBar chart also, everything is in control. And we continue taking samples and monitor the process. If anything is outside the control, then we will find assignable causes for why it might be happening. We will correct them and go back to step 1 to collect the sample and continue looking at potential assignable causes. So let's look at an example to understand this better. Here's a company, management of West Alice Industries. They are concerned about the production of a special metal screw, which is used by several of the company's largest customers. The diameter of the screw is critical to the customers. So data from 5 samples appear in the accompanying table, and the sample size is 4, is the process in statistical control. Now, this is the diameter of a screw, which means we actually can measure it, and therefore we are looking at control chart for variables. And we notice that there are 5 samples, which means the data was collected 5 times, and every time data was collected, you have collected 4 outputs from the process. So we collected 4 outputs every time data was collected. So it could be something which was collected, let's say, on a certain day between 8 a.m. The first sample could be between 8 a.m. and 10 a.m. The second sample could be between 2 p.m. and 4 p.m. The third sample could be between, let's say, 6 p.m. to 7 p.m. or 8 p.m. and so on and so forth. But every time when we go and collect this data from this production shop floor, we are collecting 4 values or 4 screws from the output. And for each of them, we are measuring what the diameter was. So these are the diameters from the first sample, diameters from the second sample, and so on and so forth. And what we have to understand is, or answer in this question is, whether the process is in statistical control or not. Okay. Now we follow the steps that we just saw. The first thing we are going to do is find the range. To find the range for every sample, we look at the largest value and the smallest value. So if I look at the first sample, this one, the largest value in that sample is 0.5097, or sorry, 0.5027. And the smallest value in that is 0.5009. Okay, so we take the difference between 0.5027 and 0.5009, and that will be equal to our range for that particular sample, which is 0.0018. We do this for second sample. Similarly, the largest value is 0.5041. The smallest value in that is 0.5020. And we take the difference that comes to 0.0021. So we continue doing that for all 5 of these samples that we've collected. So we have these range values that we see in this column. Right? So those are the ranges for each of the sample. Once we have the range for all samples, then we take the average of these 5 values. So this number 0.0021 essentially is the average of the number that we have here, 0.0018, 0.0021, 0.0017, 0.0026, and 0.0027. So now we have this value of R bar which is the average of the range, which we need to calculate the or get the R chart. Okay, so that's one thing which we want to keep in consideration. The second thing we need is the X bar. I think it's missing here. It should be X bar here. So we need averages for all these samples. So for the first sample, we have these four values. So we take the average, which is 0.5018. For the second sample, we take the average 0.500, 0.5027, and so on and so forth. So this value that you see here, it's basically average of all the numbers that we have in this column. So average of all these numbers. So essentially this is your X double bar, which we will use later to calculate the upper control limit and lower control limit for X bar chart. Now we know this table will be used for both R chart and X bar chart. Let's start with R chart. So we compute the range for each sample and the control limit. So upper control limit is D4 times R bar and lower control limit is D3 times R bar. Now we need to know which D4 and which D3 values we should be picking from this table. So we go back to this table. Now notice that what we're interested in is in the size of sample, not the number of times we collected, but in each sample, how many different outputs did we gather. So in our case, every time we were going and collecting data or creating a sample, there were 4 different outputs that we were getting. So for this particular problem, the size of the sample is 4. Okay, so that's what we're going to use. And therefore, the value of D3 and D4 has to correspond to the value of 4 that we have here. And the 4 is because of these 4, 1, 2, 3, and 4. Right? So these are the 4 outputs that we are collecting data for. So we'll use this D3 and this D4 in this formula. So upper control limit is 2.282 times your R bar. So this was your R bar, which we had seen in the previous table, and this is your D4. That's your formula. And likewise, lower control limit, this is your D3 and this is your R bar. So you get these values. That is then telling you what the upper control limit and lower control limit for R chart is. Once you have those upper control limit and lower control limit values, you use those values to construct your R chart, and this is your R chart. Within the R chart now, what you're going to do is find your R bar, which is the average of all the range, which also is something which you had obtained from the previous table here. So if you notice, there is this R bar here, this value. This is the value which will be the nominal value for your control chart, the middle value here. So you get the upper control limit from the formula, lower control limit from the formula, R bar value from the table itself. Now all these values that you see here, these 5 values, are the values of R that you have from the table. So for example, the first value that we are seeing here for the first sample, I go back to this table that we had. The first value for our sample was this one, 0.0018. The second was 0.0021. So let's go back here to the figure. So this is actually your first 0.0018, right? So that's what you see here, 0.0018. This is 0.0021, and so on and so forth. All these numbers correspond to the R values for each of these different samples that you've collected. Now, what we are trying to see is whether all the range values that we have in the table, they are within the upper control limit and lower control limit. And in this case, we notice that everything seems to be in between, and hence the process variability is in statistical control, because our charts are focused on process variability. So now we are good to move on to the next stage, which is to use XBar chart. Now to use the XBar chart, once again, we're going to use this 4 as our size of sample, because we are using the same situation that we had earlier. So for 4, we look for the value of A2, because that's the formula that we have, A2 times your R bar, and that has to be then added to x double bar, or it has to be subtracted from x double bar based on whether you're going to find upper control limit or lower control limit. So we go to this and find the upper control limit by taking x double bar, which we have in our table, which we saw in the very first part of this problem, which is what we see here, this number 0.5027, the average of averages, x double bar. So we take that number, plug it in to the formula here, 0.5027. A2 we just saw is 0.729 for sample size of 4, and then multiply it with R bar, which is 0.0021. So we get the upper control limit as 0.5042, and lower control limit will be x double bar again minus 0.729 multiplied by 0.0021, which gives us 0.5012. So we now have both upper control limit and lower control limit, so we can create this XBar chart. So that's your upper control limit, and that's your lower control limit. The values are what we just saw in the previous slide. The center, or the nominal value, is the x double bar, which we have in the chart, which we calculated for the given problem. So we're going to now substitute the numbers for each sample within this chart. So these numbers that I am circling here are coming from the table. We have found these values up front. So for example, this 0.5018 is the average for the first sample, or 0.5027 is the average for the second sample. So this is nothing but 0.5018. This is 0.5018 that you saw in the table, and this is 0.5027 that also you saw in the table, and so on and so forth. You can find third, fourth, and fifth. When we plot all of them, we see that first 4 samples are between the upper and lower control limit, but the fifth one goes outside the upper control limit. And hence, we know that the process average, which is what XBar chart is trying to find, is not in statistical control. So we need to find what could be happening here. Okay, so that's the way we are going to identify there's some issue, and therefore we have to fix it. So this is an example of R chart and XBar chart that we are utilizing. Now, sometimes what happens is that in a given problem, we will be provided with the standard deviation of the process distribution. In this particular case, that was not the situation. We actually were given just a table with these 4 samples and 5 samples, and for each sample, there were 4 outputs. So we had to find the R value, we had to find the X bar value, and then utilize it. But if we were given a standard deviation of a particular process distribution, then we have a particular formula which is slightly modified than what we saw for the XBar chart just now. So if the standard deviation of a process distribution is known, we use a formula where we still use x double bar like we did, but instead of using this A2 from a table, what we're going to do is we are going to use a z value, which comes from your statistics. It's the normal deviate number, and multiply it with the standard deviation of the process distribution. So whatever, so using the standard deviation of the process distribution and then dividing it with the total number of sample values we have, we can then determine what the sigma x bar is. And we will see this as an example. Next problem will tell us exactly how this has to be applied. But for now, as you can see, the first part remains the same as we did in the previous example, but the second part has changed. Instead of A2 times R, or minus A2 times R in this case, we have plus Z times sigma x bar and minus Z times sigma x bar, something which will be clear as we go forward. So let's take this example to get an understanding of how that works. This is a bank, and we are looking at the time required to serve customers at the drive-by window. This is something that they consider as a quality factor, and they want to satisfy customer on this particular front because they're competing with other banks in the city. The mean time to process a customer at the peak demand period is 5 minutes. So that's the mean average time it takes to process a customer when the demand is in its peak. We also have been told that the standard deviation is about 1.5 minutes. So we have information about the average for the process. We also have the standard deviation for the process. The sample size is of 6 customers. We are expected to design an XBar chart with a type 1 error, which we just is something which we want to reduce. But what we are comfortable with in this particular case is that that error should not exceed 5%, which means that we should be 95% of the time correct in terms of identifying if there is a process which is not in control. And there could be 5% times when we could be incorrectly identifying that the process is in control when it was not in control, or it was not in control when actually it is in control. Now, for that 5%, there's a z value, which is 1.96, which is what we're going to use in this problem. So we will use that z value and the formula that we had, and using that, we will have to construct the XBar chart. So after several weeks of sampling, 2 successive samples came in at 3.70 and 3.68 minutes respectively. Is the customer service process in statistical control? So first we will construct the XBar chart, that is this step. And then using that XBar chart, this question will be answered of whether these 2 numbers are within the control limits or not. Now, to answer the question, we take all the numbers that are provided to us. X double bar is 5 minutes average serving time. Sigma is 1.5 minutes. That's the standard deviation of it. The sample size is 6 customers given to us in the problem, and Z value is 1.96, also given to us in the problem. The process variability is something which is in statistical control. We are not worried about it at this point in time. We are already going into the XBar chart because the problem asks us to calculate XBar chart or find upper control limit and lower control limit for the XBar chart. To find those control limits, we use the formula that we just saw. X double bar plus Z times sigma divided by square root of n. Actually, the formula which you saw was upper control limit was X double bar plus Z times sigma X bar. And that sigma X bar is sigma divided by square root of n. So this formula essentially has substituted that. So X double bar plus Z times sigma divided by square root of n. That's what you see here. That's what you see here. So X double bar is 5, Z is 1.96, sigma is 1.5. That's all given here. And the sample size is n is 6. So we are just substituting all the values that we know from the given problem into this formula to get upper control limit of 6.2 and lower control limit of 3.8. We use these two to construct our control chart. Now, we know that these 2 numbers, any serving time that we have should be between these 2. So we go back and look at that last part of the problem, which is asking us whether 3.70 and 3.68 are these in statistical control or not. So 3.70 and 3.68 are the 2 numbers. So if I look at these 2 numbers, we know that if the range is between these 2, both these numbers are actually going to be lower than the lower control limit, right? So this lower control limit is 3.80, which is higher than your 3.7 and 3.68. So if I were to plot, it will look like this. Upper control limit, which is 6.2, lower control limit, so LCL, which is 3.8, and let's say the nominal value, the center of this is your 5 minutes given to us in this problem here. And 3.7 and 3.68 will both be actually outside the control limit. Both of them are outside. So the question is whether the process is in control or not, in statistical control or not. So actually the answer is that the customer service process is really not in statistical control because it's outside the control limit. But then the question one has to ask is it in a bad way outside control or in a good way outside control? We see that these 2 are actually less than lower control limit. The serving time is lower than 3.8, and lower serving time actually is good for a customer will be satisfied with something which is better than what we already had as our statistical process control limits. So in reality, it's out of control, but the new process is an improvement to what we already had. And hence, this organization needs to find ways to determine what exactly is the assignable cause for why we are having these two numbers lower than that. So this new process that we have established um, probably is helping us get the customer service even in a faster way. And we need to incorporate that as part of our standard operating practices, and then reconstruct our statistical control chart, process control chart, and see if we can continuously deliver service which is of these kinds of values that we just saw. So the objective of statistical process control is to know if the process is in control or not. And if things are outside control, sometimes it actually is highlighting that you are doing things better than what you had established your process control chart for. And there are some assignable causes that you may want to identify why things are going much better than what you thought, and then reconstruct your upper control limit and lower control limits based on these new numbers that you're seeing as part of your sample. So in this lecture, in this presentation, you went over these ideas about control charts, how we create these control charts for variables, and the process, the mechanics of calculating upper control limit and lower control limit. Thank you.